So our goal is going to be able to get data to fit in your line. Did I talk you through the turning your diagnostic on to the R squared value?
You did, but I don't.
You only have to do it once.
I don't think so.
Okay. So in order to do that, it's very useful to have on. You're going to have your calculator. Go to catalog, which is right here.
Where?
Down here. So you're going to hit yellow and then this. You hit D right here, so that's the green D. It jumps directly to the D's. Scroll down until you see diagnostic on. Push enter, enter, and done. I think it's already on the CID. I'm not positive, but I'll have to look at that. Go to catalog. Hit D to jump to your D's. Good. Scroll down to diagnostic on. Push enter, enter. What this is going to do is that when we do this regression, it's going to give you an R squared value, which is basically a thing of saying how good does the data fit the line it's creating for you. Now, different types of regressions we're looking at is linear regression. So if you look on push stat on your calculator, I say stat, calculate. Here's our list of regressions we're going to be looking at. So what is a linear regression going to create? A line, yeah. So if your data when you're doing scatter plot is in a straight line, we do a linear regression. So this means you say you've got points like here, here. If your points look something like that, you probably want to do a linear regression. Next one, quadratic regression. What do you think that is? Yeah, if it's parabolic shape. So if you had stuff that maybe data looks like that. If you did the graph of it, or did the regression, you could probably come up with this equation that would fit this. This is our goal, is to be able to fit our data to, or get a line that fits the data, depending on what type of data we have. Okay, cubic regression. What is cubic regression do you think it looks like? Cubic graph, right? And then there's also quartic, the calculator can do. I'm not going to bother drawing that up because everybody should know what the shapes look like, right?
Cubic and quartic is saying it's more maximum.
Well, yeah, you have more curves.
Okay.
So your cubic would do something like this, or fit something better like that. Quartic, maybe something more like that. There's also logarithmic. So in here you see ln regression. This is a logarithmic regression. So this would be for when your data says maybe something like that, where it follows sort of the course of a logarithm. Next we have exponential. So I'm abbreviating it the way your calculator abbreviates it, so you can just recognize that. So we got EXP regression. What does an exponential look like? So something along lines like that. So we get there, and see two more. Power regression. So this one gives you an equation of this form. Y equals A times X to the B. So it can be used in a lot of different cases. But remember, what is X to the B do? If B is less than 1, or between 0 and 1, what shape can it be? you might get something like a square root graph, cube root, something like that. If e is greater than 1, you can get parabolas or different forms of something like that. And the last one, logistic.
What would the graph be?
It's a variety of them, so that's why I'm not drawing the graph.
Based on what B is?
Yeah, based on what B is. You can have a variety of shapes. It could, yeah.
B is a variable?
Well, X is a variable, so the regression is going to tell you A and B. So X is still your variable, but remember, if you had X to the 1.5 versus X to the 1.6, X to the 2, you could all do all those with this one. Logistic is a bit more interesting. Notice, if you do a logistic regression, it's not going to give you an R squared value because it's done differently. It's not a true regression. A graph looks something like this. So the equation is going to give you something that does this. What might this be a model of? Yeah, population is one of the big things. When you look at population, you might start with a certain population, and let's say you had a really good year, you've got lots of food. The population is going to go up. However, it will max out at a certain point. And if you were watching like prey and predators, they're going to follow this, and the prey is going to go up first, then the predator is going to go up, the predator goes up, therefore the prey is going to start to go down after a while. But this is saying, we're going to increase population until we meet the satiation point where everybody's got exactly what they need, but we can't grow because we're dying just as fast as we're increasing. Sorry, okay? So we're going to input some data and then look at some of the regressions of it. So turn your book to let's do page 201. And I want you to enter in the data at the top where it says internet usage. So enter the data, you're going to go to Stat, Edit, and put in the numbers. And I would suggest do years since 1990. So for 1991, we put in 1, then 2, 3, 4, 5, 6, 8, 9, 10. And then for the other one, I'm going to, hold on first. So you go to stat, because this is exponential, so we can go down to our exponential one, right there, push enter, enter, and it should give you the equation, or the numbers that you plug in to get the equation. So 0.4431, or yeah, 332 times 1.696 raised to the x. And a 0.99 is a very good fit. Now, if you want to see the graph of this data, you go to Window. What is our lowest x we entered into the table? Probably was 1, right? So I'm going to put 0 here. The highest was 10, so I'm just going to put 12 so we get a little bit of extra room. What was the lowest y?
1.
So I'm going to put 0. Yeah. What was the highest y?
7.
So I'm going to put 80, just give us a little bit of extra room there, and go by 10. Yeah, no, nothing shows up. Oh wait, I have y.
Where did it go by 10? Oh, that's good.
So the y scale. That basically just tells us how often or where are these marks going to be. So this mark right here is 10, 20, 30, 40, and so on.
It's not bad.
Yeah. So you should get a graph. So now look, we can go up and turn those on by going up to plot. Push up here, push enter, now plot 1 should be darkened, and you graph it, and you should get your data.
How do we tell if it's exponential? Like, do we change the graph in this way?
Yeah, you look at the graph and say, this looks like it's exponentially increasing.
No, like, how do we know if we hit exponential if we did it before?
Well, no. That, when we did the exponential there, that didn't have any effect on this. On what showed up.
Graph it and then,
You can graph it and then say, what sort of equation does it look like it's going to fit this data?
why do we use that thing with the R squared?
Okay, that's basically, so let's go back here and look at, let's say we wanted to do, oh, we think this looks like a line. Clearly it's not, but if you were confused and you had the points graphed along, let's put it to a linear regression.
Why
Okay.
do we use that? For like the answer or something?
Yeah, when we're looking, if it's asked for the equation, or asked for a model, the equation is a model. Now, look at our squared values here. 0.8057. Not very good model.
It's supposed to be 1, right?
The goal is the closer to 1, the better. So linear regression really is not a good model for this data. We did the exponential model, it was 0.99, which is a really good model. Let's say if we did a quadratic regression. 0.98, so it's better than the linear model, but the exponential is definitely better. Let's go down and if we did a logarithmic. 0.54. Logarithmic, very, very bad model. In fact, it's not even good enough we could call it a model of the data. But this is if we were doing logarithmic, this would be the data that fits it best. And let's see, power. So power 0.86, also nowhere near as good as the the exponential model.
So we do that to see if the model that
How good the model
is correct?
Yeah, most of the time in the book it's going to say use the logarithmic model or use this model. And this is a way, if it says choose a model that fits best, our square value is a way to tell which one is best fitting. Yeah.
Oh, like, is there anything without, like, remembering all of those numbers to make that correct?
On the T83, I don't believe there is. On the T84, there is.
I'm trying to find it again.
Yeah, the 84 there is. I don't think there is in the 83. I don't know. I don't remember how. But I believe there is a way to transfer it over. Yes. Did you read that?
No.
Okay. So. So when you're linearizing data, it means you're taking curves or stuff and applying an operation to it to make it so they appear to be in a line as opposed to curves. So, thankfully there's some really easy ones. If you're doing a quadratic, if your points yield a quadratic, Carol, what does a quadratic look like? A parabola. What you can do is take all your points and do this. So, in other words, if you have your points, each one of your y's you take a square root of. And instead of graphing x, comma y, you're going to graph x, comma square root of y.
How would we, like, put that data in?
So you would put in square root of whatever number in each thing. Yeah, so, well, hold on, I'll show you what's exponential. The next one?
Why does it say for example natural log of y?
Okay, that's what it's going to do. For exponential, which is the one we just did, we said we graph, instead of x comma y, we do x comma natural log of y. So now, if we were doing this using the data we had before, turned on, and our stat, edit. So I know the first one is 1, so I'm going to put in ln1. Then ln of 1.4, and so on, going down. So putting in, insert, oops, that's not what I wanted. So we want to do it and put in the natural log into each case.
For exercises 18 through 21,
Mhm.
you want to graph it on paper or
Yes.
calculator?
So you'll be doing it both, but yes, you draw the graph on the paper. And assuming I've not made a mistake while I'm doing this, the data should now be linearized. So notice, the highest number is now 4.2, so I'm going to change my window a little bit. Instead of going all the way to 80, maybe go to 8. And it's much more linear than it was.
Can you change the y-scale to 1 again?
Yeah, I changed it back to 1. So now, if I do a linear regression of this, of my new data that I've created, that I've done, linear regression, the linear fits pretty well, 0.98.
How does how do you know it's linear?
What do you mean? The process that we're doing is linearization, making it linear.
But it doesn't really look like a graph.
Well, it's not going to look like the other graph, because this applies process that made it linear. So it's not going to look the same. Now, we've got a couple other things to linearize. Like if you have exponential, we do that one. If you have logarithmic, what do you think you're going to do for logarithmic? Without looking at your book.
Log of y?
Okay. Not log y. No, it's a good guess though.
Y raised to x?
It's also a very good guess. And that one I believe would work. But instead what we're going to do is take the log of x, or natural log of x. Basically to make the x's smaller. But yes, raising to the 10, or 10 raised to it, should work as well. However, then you get really big numbers. And we'd rather have the smaller number.
Graph are looking the same?
It should look very, very similar, if not the same.
What's the point of this?
To make a straight line as opposed to a curve.
Oh, okay, that makes sense.
So, in the last one, power. For this one, you do natural log of x and natural log of y. Can I do what? What? The cube root? Oh, cube root. Yeah, if you're doing a quadratic, a cubic one, yeah, you do a cube root. No, each one of these we're doing basically the opposite operation. Ellen, natural log.
You just put that in.
Yeah, and instead of having y, you're going to do the natural log of y. Now, sometimes it's easier to use this to create your model. So you run into a new symbol that you probably haven't seen before. So let's do this data. So 0.5 to 1.5. 0.5 is 0.13. Then 1, 2, 1.5, 10.1, 2, 32, 2.5, 78.1, 3 gives us 162, 3.5, 300.1, and 4, 512. This is going to be a power model.
How do you know?
Because I'm telling you.
Oh, yeah.
The book would probably tell you. Like if you look at the problem 19 through 21, it says what model to use, right? That's what I mean. I'm telling you, it's going to be a power model.
Was it closed before?
What do you mean? Oh, there, I just have those four.
Is it not linearized? Oh, no.
No.
It's okay.
So the first thing we want to do is linearize using a power model. So what we're going to do is this symbol. This is called, we call it X hat. X hat. So X is wearing a hat. So in this case, we're saying X hat is equal to the natural log of X. Y hat would be the natural log of Y.
Why do we need those numbers?
To say that we're going to do a model using X hat and Y hat instead of X and Y. Because this is our X here, this is our Y. Now we're going to go through and linearize this by finding X hat and Y hat for each of these.
Oh, this is how, like, you want us to write it down?
Yeah, this is a good organization method. Now, somebody want to start giving these numbers, natural log to the top and natural log to the bottom. So, natural log of 0.5. Anybody have it? Come on, somebody.
Negative 0.69.
Negative 0.69, okay. Natural log of 1. Everybody should know this, right?
0.
0. Natural log of 1.5.
0.41.
Okay. 2.
0.69.
2.5.
0.92.
3.
1.10.
3.5.
1.25.
4.
1.39.
Okay, so now we're going to do y hat. So natural log of 0.13. Zero 4. Okay, natural log of 2. Okay, natural log of 2, 0.69. Natural log of 10.1. Natural log of 3.2. Oh, it is 32, yes, 32.
Why did you give me 5 times 11?
Yeah. If you put a decimal in, it will actually, it'll sort of actually give you one decimal. So for example, if you put in natural log of 32 and put a decimal.
3.47.
3.47. Okay, and then the, which one is that? The, okay, 78.1. 78.1. Okay. 162. What? 5.09. Okay, 300.1. Okay, and 512. Okay, now, enter the data into your calculator. 11, yes. I was thinking 1120. So anyway, what you're going to get, if you did this, we're going to get something like y hat equals a x hat plus b, or plus in that form, right? And then we can change it to natural log y equals a ln x plus b, e to both sides, so we get y equals e to the x ln x to the a e to the b, y equals x to the a e to the b. And in here you can get a and b, you have to use your linearization term.